Dear students, today we will discuss the chapter that is integration of remote sensing, GIS and GPS. So, in this, if you look at the study outlines, you will able to understand the definition of remote sensing, GIS and GPS, and also you will get familiar with and able to know the models of the integration. And finally, you will able to know the advantage of the integration of remote sensing, GIS and GPS. Then we will look about what is a remote sensing, geographical information system and GPS. These are the generic technologies, and all these technologies are spatial in nature and mainly used in spatial applications, and most unique features of these technologies are that all are in digital form. Due to this, integration of the GPS, remote sensing and GIS can be performed and used as the basic operations and modeling. We need to study the basic definitions and concepts of remote sensing, GIS and GPS so that we can understand the principles of integration. Now, let us look first regarding the remote sensing. So, as you know that the definition of remote sensing is the science and art of obtaining information about an object or area or phenomenon through the analysis of data acquired by a device that is not in direct contact with the area or feature or phenomenon under investigation. This definition is given by Lillesand and Kiefer in 1994. So, look at that presentation. Now, you can observe that the sun is the source, and sun is emitting the electromagnetic energy and it is passing through the atmosphere and it reaches to the target, that is on the ground surface. Then after reaching the target, some of the energy will be observed, some of the energy will be transmissive, some of the energy will be reflected, and these reflected energy or these reflected electromagnetic energy which passes again through atmosphere and it detects in the sensor which is mounted to the satellite or aircraft. These we are calling as the remote sensing. So, in this way the electromagnetic energy will be recorded in the sensor and this will be converted into digital numbers, that is DN numbers, and finally we can make the aerial photograph or the satellite imagery will be the product from this remote sensing. And if you look at the advantages of remote sensing, it provides a synaptic view, means the area covering data. It also includes, already we discussed about the photo, or we can also call as image data. Now, image data acquired by remote sensing relate to electromagnetic properties of the earth. In principle, remote sensing provides information about upper or millimeters of the earth's surface. Some techniques, specifically by using microwave domain, you can also relate to greater depths of the study. And the advantage of remote sensing is that it is specifically suited for that are difficult to access, or we can get the photographs or satellite imageries of inaccessible areas. So, and another one advantage is that remote sensing provides multispectral data, means you can have the what is called as black and white satellite imagery or photographs, or we can also get red band, the green band and also the blue band. So, by this we are calling as multispectral data. Why we use multispectral data? Because some of the objects or feature not visible in one band, that will be visible in another band. So, this is the advantage of remote sensing. And then multi-purpose, once if you have taken the satellite imagery or aerial photograph, that can be used in different applications. And another one is that it is a cost effective, means if you are doing the survey, it will take a tedious and also it is a time taking, but with remote sensing it is a cost effective, and you can also have multi-temporal data. This is the advantage of remote sensing. Like for example, now you can get the images of 2024 data, 2025 data, like that you can have a number of time period data also available. So this will help the what is called for analysis or the spatial data. Now next one is that the remote sensing requires ground data. Although remote sensing data interpreted and processed without other information, but the best result obtained by linking remote sensing measurements to ground measurements, which are obtained by global positioning system, that is called as GPS or other techniques, and data will be generated through GIS, whatever we incorporated into the GIS. So now what we can say that remote sensing singly we can use this, but the best results will get when we use the or when we integrate the GPS with the GIS. Then the another technology that is called as geographic information system, that we are calling as GIS. It is referred it as a powerful set of, we can collect the spatial data, we can store the spatial data, we can retrieve the spatial data, or we can transform the spatial data, and finally we can display the the real world for a particular set of purpose. This definition is given by BRAOU and McDonnell. Here the GIS draws on concepts and ideas from many disciplines. It mainly disciplines as a diverse as geodesy. Geodesy is a one important thing, and photogrammetry, remote sensing and digital surveys also this comes under. In GIS we can get the ideas from many disciplines. It mainly involves the fundamental issues arising from the creation, storage and usage of geographic data. So look at the figure here. Now the figure is showing about the different disciplines which is used in geodesy, photogrammetry or remote sensing. And next one here, GIS operates primarily with the 5 components which are very important for the GIS. That components are hardware, software, data, people and methods. So these 5 components are very important to operate the GIS. So in the figure you can observe that these are the components which will run the or which will be used for the process of GIS. It is a crucial to have a good understanding what a GIS can do and is working with. And then there is a wide variety of data sources, and all data fall into one of the 2 categories. So everybody knows that it has primary data and secondary, and these data have 3 modes or dimensions, that is temporal, thematic and spatial. Here current GIS systems can handle 3 or 4 dimensions as well as objects. Most can now support both raster and vector data. So look at the figure. Now the GIS database you can divide or categorized into spatial database and non-spatial database. So what is spatial database? Which is regarding the information of the earth surface or features or the objects, and non-spatial data which is attribute data, we can call as attribute data, which will specify the spatial data, that is called as non-spatial data. For example, what is spatial data and non-spatial data? The river is flowing, the image of the river which we can see, that is called as the spatial data. Now the name of the river, the different distributors of the river, that all comes under in non-spatial data. Non-spatial data is also called as attribute data. Now these spatial database have the 2 data structures, one is raster data structure and another one is vector data structures. So raster data structure is stored in the form of rows and columns, that is the minimum unit, that is called as 1 pixel. So it represents the storage of the spatial data. It is in the form of matrix of cells and columns. And vector data is nothing but it is consists of xy coordinate, like we can categorize this vector data into point, line and polygon. So what is point here? The point is nothing but the x1, y1. And what is line here? x1, y1, x2, y2, x3, y3 and xn, yn. So, this is representation of vector data. And what is a polygon? In polygon, the starting point and ending point will be the same, x1, y1, x2, y2, x3, y3, or the another end point will be the xn, yn will be equal to the x1, y1. So, this is a vector data. So, now you can understand that GIS database has spatial and non-spatial data. So, the spatial data again you can store in the form of raster form and vector form, and again vector form it will be point, line and polygon. In the similar manner, the non-spatial data is stored in hierarchical data structures, network data structures and relational data structures. Then another technology in spatial technology, that is called as global positioning system. The global positioning system is a satellite based navigation system that is built up by network of 24 satellites placed into orbit by the US Department of Defense. Now, it is an all weather, means in all weather conditions it will work, and it is a space based navigation under the development by the Department of to satisfy the requirements for the military to accurately determine their position, velocity and time. These are the important, and which is in a common reference system. This is very important. It should be in a common reference system anywhere or on the earth continuously. This is definition which is given by Wooden 1985. Now, if you look at the GPS consists of three segments: the space segment, control segment and the user segment. So, the US Air Force develops, maintains and operates these all the segments. Now, space segment comprises a nominal constellation of 24 operating satellites that transmit one-way signal providing the current GPS positioning and time. Means if you look at the space segment, it is 6 orbits we can see on the Earth's over the Earth's surface, and these 6 orbits, each orbit is having 4 satellites. Totally 24 satellites are launched specially to get the positioning or timing or to know the velocity. And the another segment is the control segment. The control segment consists of worldwide monitor and stations. It tracks the GPS satellites, the uploads and updated navigational data and maintain the health status of satellite constellation. This is also maintained by the US Air Force. And the another segment that is called as user segment. User segment is nothing but the GPS receiver equipment. It receives signals from GPS satellites and uses the transmitted information to the users in 3-dimensional positioning and timing. So, in 3-dimensional means you will get the latitude, you will get the longitude and also you can the height, and also you can know the time and velocity. Then now the next question is that we already know about the technologies remote sensing, GIS and GPS. So, now we will see the integration of GIS, GPS and remote sensing. Despite its various development, GIS distinguishes itself from the other two technology in that it can enable from diverse sources to be integrated, analyze and model its powerful analytical function. Now, GIS database may be incompleted, outdated or generalized due to the what is called rely on old maps. For example, I will give the one example here. Now, you have a map of 1980s. So, if you want to make a planning on particular that map, so that data is outdated. If you plan by using that map, you cannot get the reliable information. So, what is needed here? Here you need a up to date information or original data or present data. So, here at this juncture remote sensing and GPS overcome these limits by providing the original, up to date and spatial thematic data. So, especially aerial photographs, satellite imagery and GPS based surveys ensure accuracy, timeliness and also efficiency in building reliable GIS data sets. Now, remote sensing is fundamentally, we have seen that it is for data acquisition using photographs or satellite images that are geographically referenced to the coordinate system. To enable comparison, integration and overlay with other dataset images must be georeferenced to a standard or universal system requires geometric control points on the ground. The geometric control points on the ground is nothing but the GCPs. So, now geometric or georeferencing is must for the satellite imagery or aerial photograph. Traditionally, such control has been derived from topographic maps. They are widely available and geometrically reliable. However, reliable on topographic maps has limitations. In regions lacking distinct landmark where landscape have undergone significant changes, since the map as published they prove ineffective, making alternative georeferencing is essential. Now, at this juncture, GPS provides spatial data that is automatically referenced to an uniform coordinate system and can capture point, linear or aerial data in real time. Now, ground control point GCPs from GPS are often used to georeference remote sensing images. However, GPS alone cannot replace the accurate satellite imagery for accurate aerial data. Remote sensing, GIS and GPS are therefore complementary and individually limited. They reach their full potential when integrated, enabling efficient spatial data management, resource monitoring and time what is called as time emergency responses, which proves specially valuable in applications such as wildfire management and environmental monitoring. Now, let us see the integration of remote sensing, global positioning system and geographical information system. These three technologies are the backbone of modern spatial science. Each has its own strength. Remote sensing provides imagery and spectral information about Earth's surface. GPS provides accurate location and navigation information, and GIS stores, analyzes and models spatial data for decision making. To combine their strengths, scientists have proposed 4 models of integration. One is linear model, and another one is interactive model, and hierarchical model and complex model. So, let us discuss about each model in detail. So, look at the figure here. Now, the linear model, the data flow will be from the what is called as in one way, that is from GPS to remote sensing, where the georeferencing is the one, and remote sensing to GIS. So, now this is only one way, that is from GPS to remote sensing, remote sensing to GIS. So, each component contributes its unique strength, with GPS providing the control for aerial photograph or satellite imagery. These rectified images stored in GIS database. And then GIS plays a dominant role as a final destination where all spatial and modeling occur. GPS has a subordinate role, supplying only point based data only to support the remote sensing. In the final GIS database, GPS data are not directly visible, but as a crucial bridge in bridging the standardizing imagery to the georeferencing system used by the GPS. GPS and remote sensing integrate in 3 temporal modes. One is simultaneous mode, independent mode and post-processing mode before linking with the GIS. In simultaneous integration, GPS mounted on aircraft aids navigation, sensor parameters, guide flight paths and record the photo coordinates and efficient rectification and aerial triangulation. Independent integration georeferences pre-acquired images using GPS coordinate with accuracy influenced by number of GCPs, differential correction and receiver quality averaging multiple GPS reading enhance the precision. The last one is post-processing integration occurs after image analysis, where GPS versus land cover maps are detected changes through field surveys. Portable GPS guide ground visits, improving map accuracy and supporting environmental land use studies. Then the another one is the interactive model. You can see this on slide. Here in the interactive model, it resembles like a linear model, but allows mutual flow between the GPS, remote sensing and GIS. You look at this look at the image. GPS coordinates, which is used in the georeferencing of remote sensing images, and again database conversions can be from remote sensing to GIS database. Here again the remote sensing is used for GPS coordinates and GIS is used for remote sensing. So in this way there is a mutual what is called as transfer between GPS, remote sensing and GIS. Remote sensing is no longer just a data source, it is integration may occur in a image analysis system such as radar imaging. GIS and remote sensing share equal significance, while GPS plays a modern role, but its data can be directly visible in GIS. Now if you look at the interactive model, GPS overlay can enhance remote sensing results such as mapping or roads that are not visible in a coarse imagery. Example, I will tell that. So if you have a satellite imagery, but in the satellite imagery there is a coarse resolution and fine resolution. Fine resolution you will have a clear image, but in coarse we cannot see the clear image. So the roads we cannot see. By integration GPS we can also see the roads in the satellite imagery. Now application include land cover change detection, image segmentation and classification, utilizing GIS knowledge to improve accuracy and enable analysis such as impervious or pervious surface estimation. The another model, that is hierarchical model. The hierarchical model operates in two tiers of integration. So the first tier is overlays and the second tier is modeling. What is the first tier? Here it links the GPS data with remote sensing imagery. Here derived coordinate rectify remote sensed images and help to characterize the samples based on their precise locations. Overlaying these samples with the imagery or digital photograph establish the relations between the ground verification through the image properties. So this is the first tier, that is overlaying. The second tier, that is modeling, combines remote sensing data with the other data sets and mathematical models we can see in the second tier. Depending on the data format, modeling performed in GIS or a digital image analysis system particularly affect the raster based solutions. The another one is hierarchical model. Unlike the interactive model, GIS and remote sensing are not connected. Instead, remote sensing plays a dominant role by supplying data for monitoring and modeling. GIS contributes supplemental data and may provide the analytical framework. GPS retains a subordinate but extended role, aiding the first tier but not influencing the second tier. You can look at this figure. This is the GPS and this one is remote sensing and this is GIS. So here for overlaying, GPS and remote sensing is used, but for the modeling your remote sensing dominates. So the modeling can be done all this through the GPS overlaying, modeling and through GIS. Then the another method, that is called as the complex model. Here you can see in the figure, the complex model is that it is in a cyclic way. GPS used in remote sensing or the data with remote sensing can be used in GIS and GIS again with GPS. In this way there is a cyclic what is called flow of data we can see in the complex model. It is a most advanced model. All three components interact each and every possible way. Here the key features are GPS, remote sensing, GIS plus direct GPS GIS connections we can see here. So I already said that there is a circular integration. Any component can be most important depending on the application. GPS data, point, lines, polygons can directly update in the databases. So I will give one example for this one. Application example is precision farming. You know precision farming. this is the forming in way that we will use remote sensing, GIS and GPS for the what is called technology. These technologies are adopted. So, suppose in the precision farming you will have a GPS driven tractor. So, if you reach one place, so it will show the complete map of that particular area and also the location of particular area. So, by using this precision farming you can get the higher crop yield, and also you can have what is called as it provides a large scale monitoring we can do through the precision farming. And look at this figure. I have given this differences between what is linear, it is one way, interactive is a two way, and hierarchical is a two tier, and complex is full circular. So, in linear GIS is dominant, and in the interactive RS and GS is equally shared, and hierarchical remote sensing is dominant, and in the complex depends on the context or depend upon the survey, these will be used. So, example of use is in linear aerial photo rectification, in interactive land cover change detection, and in hierarchical vegetation monitoring, and in complex precision farming. These four models that is linear, interactive, hierarchical and complex, different levels of integration. The choice of model depends on the research objective. Over time the trend is moving from the simpler, that is linear, to complex, which is integrated, especially with advances in computing and field based technologies. Now, let us see the some of application and prospects of integration of remote sensing, GIS and GPS. The integration of remote sensing, GIS, GPS supports a wide range of applications in resource management, environmental monitoring and emergency response, and mobile mapping. In natural resource management, remote sensing provide data for forest resources and precision farming, while GPS improves rectification, ground and sampling accuracy. Now, here applications include vegetation mapping, groundwater assessment and cropland monitoring, and coniferous habitat suitability analysis. For an emergency response, GPS and GIS enhance real time navigation and also fire management through equipment tracking, fire perimeters and post fire rehabilitation planning. Integration also strengthens storm warning, flood prediction and evacuation strategies. So, the another important component is the application is mobile mapping. So, in the mobile mapping, GPS, digital cameras and navigation sensors, vehicles, vessels or aircraft collect the georeferenced images from various mapping, photogrammetry or utility service. These systems capture accurate spatial and multimedia data efficient. So, these are all the things and prospects for integration. The future of integrating GPS, remote sensing and GIS holds a possibility, particularly with the development of location aware what is called personal digital assistants, PDAs, and distributed mobile GIS, that is DMGIS. A location aware PDA is essentially a handheld computer with a GPS capable of storing GIS data such as roads, tourist attractions, and also application include vehicle navigation, route planning and the guidance.